learners. It is always a pleasure to have you, and we are always excited that you're doing well also in your subjects. We thank you for your feedback. Thank you that you are enjoying these lessons. In our last session, we looked at what we call reverse biasing and also what we refer to as the PN junction diode or a semiconductor diode. Let me just recap on the PN junction diode, whereby we say it is also referred to as semiconductor diode. And we say the PN junction diode, or a diode as we'll be able to see in our connection, is a component in electronic or a device that acts as a one-way conduction device, meaning it allows current in only one direction. So that is what we say, it's like a one-way gate. And we also mentioned about the symbol of our diode, which we said looks like that. So we got an arrow-like, and then we have that circular thing like that. So we say the arrow points in the direction of flow of conventional current, whereby this is the anode, and then on this side we have the cathode. So we also mentioned that it is possible to forward bias the anode such that when you connect the anode of the diode, which is the P-type side, to the positive terminal of the cell, we say that is forward bias. When you interchange such that the anode of the diode is connected to the negative terminal of the cell, then we say that is reverse bias. Now, we want to go to another subtopic known as the diode characteristics, and we'll try to look at an experiment that is normally used to investigate the characteristics of a diode. Now, in this experiment, all we shall be using is a diode in itself. We'll be talking about probably a silicon diode. We'll have a rheostat, or what we refer to as a potentiometer. We'll be having a milliammeter because of the small amount of currents that are generated. Also, we'll be having a voltmeter, a cell, and preferably a 2-volt cell or a 2-volt accumulator, and of course an optional device. This is optional. It could be a 10-ohm fixed resistor. So that is what we'll be having, and of course then we can be able to arrange these and see what do we expect in this particular experiment. So here we'll be having a few apparatus. One, we have said we'll be having a diode. So a diode, we'll be having a rheostat, or what we call a potentiometer. So this is what we refer to as a variable resistor, or you can use another one that is common, a potential divider. We also need to have a cell or an accumulator of 2 volts. Accumulator of 2 volts. Again, of course, we require to have a milliammeter. Milliammeter. So milliammeter. The ammeter should have a double M. Milliammeter. We also need a voltmeter. And optional here, you can have a 10-ohm fixed resistor, and we'll be able to say why this is important. This is fixed resistor. Optional. So that is optional. Now, In some circuits, you'll find that we don't have a fixed resistor, but we'll say why it is sometimes good to have a fixed resistor. This one is for the safety of our diode. So the fixed resistor, we can say here, the fixed resistor acts as a safety resistor, acts as a safety resistor. This one protects the diode by restricting the maximum current that can flow. By restricting the maximum current that can flow. So this is very important because one of the things we'll come to see that it is possible to break a diode. So a diode can reach a breaking point whereby it is actually destroyed. So it is important that sometimes we have a safety resistor. How will that circuit look like? So we need to look at how the circuit will look like. So we'll have circuit. Let me just draw. We try to insert the rheostat. Our rheostat, that is the symbol of our rheostat. Then we have our safety resistor. So we'll be able to label them. Of course, the ammeter is connected in series. So that is our milliammeter. And of course, we have the source of EMF, which is our 2-volt cell. And on this side, we can have our diode, forward biased. So looking at our cell, then our diode is forward biased. And of course, every time you are connecting a voltmeter, you connect across the load, so that is where the voltage drop actually occurs. So we have our voltmeter across the diode. That's what we'll be having there. So we have that set up. Then we can be able to label that. We can be able to label that. I'm looking for a blue pen. So this is our rheostat. This is the safety resistor. This is the milliammeter. Of course, that is our diode. This is our voltmeter. And this is our 2-volt cell. So that is done. So how do you go about it then? How do you go about looking for the characteristics of a diode? So I'll be able to give you the simple procedure and what you're supposed to do. And then, of course, we'll be able to explain the observation in the next lesson and probably give you some rough or data that you can be able to plot and confirm some of these things that we will be mentioning. So the first thing you're supposed to do is to adjust the rheostat So adjust the rheostat to vary the forward bias voltage. To vary the forward bias voltage. So you adjust the rheostat to vary the forward bias voltage. VFB, so that is our forward bias voltage. And that one you can be able to see from your voltmeter as you adjust the rheostat, which is our variable resistor. So you can be able to check the values of the current and the variation of the voltage. So you want to vary so that you have an increase. But of course, we'll be having some gradual incremental so that we don't destroy our diode. So forward voltage like that. This one will be across the resistor. Of course, it is across, not the resistor, but across the diode in steps of 0.1. In steps of 0.1 volt. We'll be able to see why. Because the current generated is very small, as well as the voltage. Sometimes you want to get at least some varied data so that you can be able to do some plotting. Of course, when you adjust and get the forward bias voltage, you will be able to also see a corresponding current through the diode. So that will be seen on the milliammeter as the variation of voltage, as the voltage varies, also the current will be changing. So record, so you record the values of the corresponding current through the diode. Record the values of the corresponding current through the diode. So that is very, very important. And finally, after you do that, this one will give you a form of a table. So how you'll be able to record that. So you have current. Remember, current is measured in amperes, and the current, the symbol is I. So you have I in milliamperes, and then of course you have the forward bias voltage in volts. So your table will look like this. So this will be your table, and of course later on I'll give you values that you can be able to practice with and get to apply the knowledge we talk about. So that is what you will be having as an example of the data where you record your data. Then once you will have the data, you're supposed to plot a graph of current, that is current I in milliamperes against forward bias voltage. So against VFB, and that will be in volts. So that will be the side on forward biasing. So remember, this is forward bias. Then we want to interchange or reverse our diode, or we can also reverse our cell. So one of that will do. You can change the terminals of the diode so that it is reverse bias, so that the negative is connected to the positive, or you can change the direction of the cell. So the next thing, so we'll be looking at that in a short while, and then of course we'll see what happens. Reverse the connection. Reverse the connections or connections to the diode. So reverse the connections to the diode. So this is what we mean by reverse bias and repeat the current and voltage measurements. And repeat the current and voltage measurements. As we said, is that you will be able to get values. You will get values which we say that the conduction in this case will be a result of what we refer to as minority charge carriers. So that's what we say. So then, of course, when you do that, you again plot you record your data. So you can have a table to record your data. So this is the format we'll be having. So you'll have a table like that, and of course you'll be having your current. So it's important, you can also say this is forward biased current. We have reverse biased current in milliamperes, RB. Also we have reverse biased voltage in volts, and of course your data will be put there. Now, once that is done, then you're supposed to plot a second graph. So plot a second graph. So with the data obtained, plot a second graph. Plot a second graph of reverse bias currents. Reverse bias current IRB in milliamperes against reverse bias voltage. Against reverse bias voltage. So that is what you'll be able to have. Reverse bias voltage with reverse bias current. After doing all this is the expectation that you're supposed to have. I want us to look at each one of them. We start with the forward bias, and then of course we come to the reverse bias. So let's look at forward bias. So this is observation. So once the experiment is done, you can be able to check what is expected. Of course, we expect that our diode will conduct. That is what we expect. So we expect that our diode will conduct. But when you plot a graph of current against voltage in a diode that is forward biased, then it is observed that this is non-ohmic because it is non-linear. So it is not a straight line through the origin like we saw for ohmic conductors. So diode is a non-ohmic conductor, meaning that it does not obey Ohm's law. So that is what we are saying. So when a graph is plotted for forward bias, when a graph is plotted for forward bias, the curve is non-linear. The curve is non-linear. That means the diode is non-ohmic. So the diode is non-ohmic. Now, you also notice that as the voltage is increased from 0, so you are gradually increasing the voltage, that as the voltage is increased from 0, the voltage is increased from 0. As the voltage is increased from 0, a very small current flows. A very small current flows through the diode. Flows through the diode because forward bias voltage. Forward bias voltage, what we call VB, a VFB, that's what we mentioned as the forward bias voltage, is insufficient in opposing the potential barrier. Is insufficient in opposing the potential barrier. So remember, we said in our discussion that there exists a potential barrier. So at the beginning, when the voltage is still low, then you notice that the amount of current that flows is also very small because it is insufficient. That is, the forward bias voltage is insufficient in opposing what we call the potential barrier. So we can note that, and you can recall we discussed all this in our build up to this particular PN junction topic or subtopic. So that is what we are saying. But of course, after some time, then of course we'll be able to see a large amount of current flowing. Now, we need to note that the leakage current, this small amount of current, is what we call the leakage current. So this small amount of current, this small current is the leakage current, and that leakage current is due to what we call the flow of minority charge carriers, which is due to the flow of minority charge carriers. At this stage, we have not yet overcome the potential barrier, so that we have now a fairly good amount of current flowing. So when the potential barrier is completely overcome, so when the potential barrier is completely overcome, so when you finally break the potential barrier, then it means, of course, by increasing the forward bias voltage, by increasing the forward bias voltage, so that is the VFB. So when you increase the forward bias voltage, then we have what we call electrons or charges beginning to flow easily across the junction. So when that potential barrier is completely overcome, so we are saying at that particular point, the forward bias voltage is what we call the cut-in voltage, or the threshold voltage, or the breakdown voltage. So we are saying that when that is completely overcome by the forward voltage, at the cut-in, so cut-in voltage, so at the cut-in voltage, so at this particular point, then you will see your diode beginning to conduct. So it will begin to conduct, and a lot of current will be flowing to the extent that your milliammeter will be recording a significant amount of current. We'll be able to see that in our sample data. This cut-in voltage can also be referred to as the threshold voltage, or what we call the breakpoint voltage, or the breakpoint. The breakpoint voltage. So we have cut-in, breakpoint, or threshold voltage. That voltage will mean that a lot of charges will begin to flow. So we can look at what we have just written. When the potential barrier is completely overcome by increasing the forward bias voltage at the cut-in voltage, then we need to say that charges easily flow across the junction. Charges easily flow across the junction. So of course, you know, the junction is the depletion layer, and we say a junction is formed when you have fixed ions that are not covered. So that is what we meant by the junction, and this gives rise to sharp increase in forward bias current, giving rise to sharp increase in forward bias current, what we wrote as IFB, forward bias current. Very important to note that. I hope you can still see up to here. Yeah, so that is what we are saying, that initially the current will be small as you adjust your potential divider or the rheostat. Then you notice that your current gradually rises from zero, very small amounts of current, but at a certain point that amount bursts, and then of course you have suddenly large amount of current being recorded by your milliammeter. That is what we are saying is the cut-in voltage, threshold voltage, or breakpoint voltage being recorded as our forward bias voltage. We can see then that in a graphical form how that explanation will be displayed when you draw your graph. So what we are saying that we are plotting, as we say, the current against voltage. So we have current, which is forward biased in milliamperes, and then of course we have our forward biased voltage in volts. And of course, as you can see, initially we'll be having very almost zero current. So at some point, then you'll begin to see a rise. Then of course it continues. So initially you'll find that there is no current recorded even as you increase the value of forward bias voltage. But then it will reach a point when your current will suddenly increase. At that particular point is what we refer to as the cut-in voltage. The cut-in voltage. So this is the cut-in voltage. Cut-in voltage. Very, very important. Now that brings us to the close of the first part on the observations and explanation with regard to our experiment that we have talked about, whereby you are determining the characteristics of a diode in forward biased mode and reverse biased mode. We have said this is how our diode will be arranged. Everything is in series, except of course the voltmeter, whereby it is connected across the diode so that you can be able to see the potential drop. You need to adjust your rheostat. We have said in intervals of 0.1 seconds, that is in steps of 0.1 volts, rather, 0.1 volts. And then as you can see from our graph,
as you increase the forward bias voltage, initially you will not be able to record any current. But slowly you'll be able to see small amounts of current, which we have said is as a result of leakage current. Then it reaches a certain point when the amount of charges suddenly increase. And then you see that our diode now begins to conduct. That point where our current has become at least of a large amount, that is what we have called the cut-in voltage, or what we refer to as the breakpoint voltage or threshold voltage. And of course, that one is what is recorded by our voltmeter. So you can be able to know that. But it's important that you understand that is how our forward bias diode will behave when connected in that particular circuit. Till we meet in the next lesson, where we'll be looking at the reverse bias characteristics by just reversing the diode or reversing the cell, one of it. It is bye for now, and I wish you God's blessing, and continue doing what we are telling you to do, because that is where you get your success. Bye-bye.